Welcome to the Deep Dive, where we take complex tech specs and, well, try to make sense of them for you, turning them into knowledge you can actually use. Today, we're looking deep inside your computer, specifically at the memory modules. You've probably seen the terms UDIMM, SODIMM, RDIMM, LRDIMM, but what do they really mean? We're going beyond the labels, our mission today, to unpack the engineering decisions behind these, the trade-offs that really shape how your system performs, how much it can grow, and, yeah, how much it costs.
Absolutely. And this stuff matters, whether you're specing out a new gaming machine or a huge server for the cloud, it's critical. And look, these aren't just like four slightly different options fighting it out. They're built for specific jobs. The core battle, the real tension here, is always balancing low latency. That's your system's responsiveness, how quick it feels against high capacity. That's about scale, how much memory you can pack in. You can't just have it all. You have to pick your priority.
Okay, let's rewind a bit then. To understand today's DIMMs, we need to start with the DDR revolution. Double data rate. Before that, we had SDR, single data rate. And the big limitation was it only moved data on the rising edge of the clock signal.
Right, which basically means half of the clock cycle wasn't being used for data transfer. Pretty inefficient.
So DDR came along and fixed that.
It did,
Yeah.
with a really neat architectural trick. DDR transfers data on both edges of the clock signal, the rising and the falling edge. So boom, you've effectively doubled your bandwidth without actually having to double the clock frequency itself.
Okay, doubling the transfer opportunity sounds good, but how did they make sure the data was, ready for both the up and the down ticks of that clock? Seems like you could still hit a bottleneck there.
Good question. That's where this term 2-bit prefetch comes in. It sounds technical, but the idea is simple. Prefetching just means getting the data ready before it's actually needed. The 2-bit prefetch pulls 2 bits of data from the memory cells ahead of time within one clock cycle. So you've always got those 2 bits queued up, ready to go, one for the rising edge, one for the falling edge. And that's actually why we talk about memory speed and MT's megatransfers per second, not just megahertz. It reflects those 2 transfers per clock cycle.
Got it. So smarter communication, not just raw speed. And the sources mentioned this efficiency drive kept going, right? Faster speeds, lower power.
Oh, definitely. That's been the constant goal. You see DDR3 hitting speeds like 2133 MTs, but then DDR4 drops the voltage down to just 1.2 volts. Getting faster while using less power is crucial, especially when we're cramming more and more memory into things.
Okay, makes sense on the data side. Now, what about the physical sticks themselves? We went from SIMMs, single inline memory modules, to the DIMMs we use today. Why that change?
That was a big one. SIMMs had a fundamental problem. Only a 32-bit data path. So when processors went 64-bit, which became standard, you couldn't just slap in one SIM. You actually had to install them in matched pairs to feed the CPU the full 64 bits it expected.
Right, I remember that. Kind of a pain if you were upgrading.
Exactly. It added necessary complexity. So the DIMM dual inline memory module was designed to solve that.
How to do that?
It's pretty straightforward but clever. DIMMs have separate electrical contact points on both sides of the circuit board. That dual-sided setup immediately gave us a native 64-bit data path, or 72-bit if you include ECC, error correcting code, which is vital for servers. No more pairing needed. It simplified things massively and really paved the way for the higher capacity modules we have now.
Okay, foundation laid. DIMMs are the standard. Let's get into the types you actually buy today. Starting with the most common one, UDIMM, unbuffered DIMM. This is what's probably in your desktop or laptop right now, isn't it?
Almost certainly, yeah. For consumer stuff, UDIMM is king. The key thing here is simplicity, which translates to speed. With a UDIMM, every single memory chip on that module has a direct, unbuffered line straight to the CPU's memory controller.
The IMC, the integrated memory controller.
Exactly. The IMC, that part of the CPU that manages all the memory access. In a UDIMM setup, it talks directly to every DRAM chip. No middleman.
And the upside of that direct line?
Super low latency. It's fast. The signals go straight there. That makes UDIMMs responsive and, pretty cost-effective, great for everyday use. But that direct connection creates the scalability problem. It's all about the electrical load.
Ah, yes, the electrical load. Break that down for us. What actually happens if you try and use too many UDIMMs in one system?
Okay, think of the memory controller, the IMC, like it's trying to shout instructions down a hallway. With UDIMMs, it has to shout loud enough for every single chip on every single module connected to it to hear clearly. Each chip adds a little bit of electrical drag, a load, add too many modules with too many chips, and the IMC just doesn't have the electrical oomph to drive that signal reliably to all of them.
So the signal gets weak, garbled.
Precisely. You get data errors, instability, crashes. It's like trying to run, I don't know, 20 appliances off one old extension cord. It just can't handle the total load.
That makes total sense. So that load limit is why UDIMMs generally max out in capacity? Like you typically see maybe 32 GB DDR4 UDIMMs, but not much bigger.
Exactly that. UDIMM is the choice for low latency, low cost, but you pay for it with limited capacity because of that direct electrical burden on the IMC.
Okay, so desktops are fine with that limit. But servers, they need way more memory. Hundreds of gigs, even terabytes. How do they solve this electrical load problem?
They introduce a middleman. That brings us to the RDIMM, the registered DIMM. This is the workhorse for servers.
Registered, so it adds something to the module.
It adds a special chip called a register. You can think of it as like a signal buffer or an amplifier right there on the memory stick. But here's the crucial part. This register chip only buffers the command, address, and clock signals, not the data itself.
Hold on, so the CPU's memory controller doesn't have to shout the instructions to every single DRAM chip anymore.
That's the key innovation. Instead of driving the command, address, and clock signals to, say, 16 or 32 individual DIMM chips, the IMC only needs to drive the signal to one target, the register chip on the RDIMM. Then, the register chip takes over and distributes those commands and addresses nice and clearly to all the DRAM chips on that specific module.
Ah, so it isolates the load. The IMC sees a much lighter load per module.
Exactly. It dramatically reduces the overall electrical strain on the memory controller, and that's what allows servers to reliably handle many more memory modules and therefore much higher total capacity.
That's a really smart way to do it. You're essentially making the connection less direct, trading a tiny bit of speed for a massive gain in stability and capacity.
You got it. And the capacity gain is huge. With RDIMMs, you see DDR4 modules hitting 128 GB each, letting you build systems with terabytes of RAM. The trade-off, like you said, is that register chip. It does introduce a tiny delay, maybe about 1 CPU clock cycle, so latency is slightly higher than a UDIMM, and power consumption is marginally up too. But for servers, that stability and capacity are way more important.
Okay, RDIMMs handle the server load well, but what if even that's not enough? What about those extreme cases, like huge scientific simulations or training massive AI models where capacity is literally everything?
Right, for those really demanding jobs, like high-performance computing, HPC, you need the next step up, LRDIMM, load-reduced DIMM.
Load-reduced sounds similar to registered. How does it go further?
It takes the buffering idea to another level. Instead of just a register chip, LRDIMMs use something called an AMB, an advanced memory buffer.
And what makes this AMB different from the register on an RDIMM?
This is the absolute key difference. Remember how the RDIMM register only buffered command, address, and clock signals?
Yeah.
The LRDIMM's AMB buffers all of those, plus it buffers the actual data signals too.
Whoa, okay, so RDIMM buffers the instructions, but LRDIMM buffers the instructions and the data flow itself.
Exactly. It's a much more comprehensive buffering approach. By isolating the data lines as well, the AMB makes the module look like a single, very clean electrical load to the memory controller, even cleaner than an RDIMM. This allows LRDIMMs to support more ranks. Think of ranks as independent blocks of memory chips on the module. LRDIMMs can handle up to 8 ranks, whereas RDIMMs typically top out at 4.
More ranks means higher density on the module, right? So you can pack more total memory into the same number of slots.
Precisely. That's why LRDIMMs enable the absolute maximum system memory capacity. They're built for density. Now, they do have the highest base latency because of that extra buffering step, and they are the most expensive option. But when you're running workloads where memory capacity is the absolute bottleneck and you need maximum throughput under heavy load, LRDIMMs are often the only choice. Think massive virtualization or big data analytics.
Okay, so we've gone from direct connection, UDIMM, to buffering instructions, RDIMM, to buffering everything, LRDIMM, to solve the electrical load and boost capacity.
Yeah.
Let's switch gears slightly. What about physical size? Sometimes the problem isn't the electrical load, it's just space. That brings us to SODIMMs, right? Small outline DIMMs.
Yeah, SODIMMs. And this is a really common point of confusion, so it's important to clarify for everyone listening. SODIMM is not another functional type like UDIMM or RDIMM. It has nothing to do with buffering or electrical load. SODIMM refers purely, strictly, to the physical size of the module. It's a form factor standard.
And the key feature is just that it's small.
Yep. It's about half the length of a standard DIMM. Roughly 67, 68 millimeters long, compared to the standard 133 millimeters or so for a desktop DIMM. The whole point is just to fit memory into tight spaces. Think laptops, small form factor PCs, some network gear, embedded systems, that's it.
So SODIMM could actually be a UDIMM internally, or even an RDIMM.
Exactly. Most laptop SODIMMs are functional UDIMMs because they prioritize that low latency and cost. But you can find SODIMMs that are RDIMMs, typically for like mobile workstations that need more capacity and ECC support. The SO just tells you it's the small version.
Okay, that's a crucial distinction. SODIMM equals size. UDIMM to MOLDIMM, function buffering.
You got it.
Right then. Let's pull this all together. We've unpacked the architecture. How does this help you, the listener, when you're actually choosing memory or looking at system specs? Let's run through the scenarios based on those trade-offs. Building a gaming rig, upgrading your home office PC. You want speed, responsiveness, and probably want to keep costs down. UDIMM is your go-to.
Makes sense. Lowest latency, lowest cost. Capacity is usually sufficient for those tasks.
Okay, scenario 2. Setting up a server for a small business, maybe running a dozen virtual machines. Stability is key, and you need decent capacity, say 128 GB or 256 GB.
That's prime territory for RDIMM. You accept the tiny latency increase because you absolutely need the stability the register provides, and you need the ability to install more higher capacity modules than UDIMM allows. It's the balanced server choice.
And finally, the big iron. You're building a cluster for heavy data science, maybe AI training. You need terabytes of memory. Maximum density and throughput under load are non-negotiable.
That screams LRDIMM. Highest capacity per module, best performance when the system is absolutely slammed with memory requests. You pay more, latency is a bit higher at baseline, but you get density and throughput that nothing else can match. Capacity dictates the choice.
And if we just quickly recap the why behind those choices, looking at that electrical load again.
Sure, UDIMM. High load on the memory controller, limits capacity. RDIMM. Low load because it buffers commands and addresses. LRDIMM. Very low load because it buffers everything commands, addresses, and data, allowing the highest density.
Perfect summary. Now, before we wrap up, there's one absolutely critical warning we need to give, especially for anyone working with servers: compatibility.
Yes, this is non-negotiable because RDIMMs and LRDIMMs handle signals differently. Remember, RDIMM buffers commands addresses, LRDIMM buffers commands addresses, and data. They are fundamentally architecturally incompatible.
Meaning you can't just mix and match them in the same server.
Absolutely not. Never mix RDIMMs and LRDIMMs in the same system, or even often within the same memory channel depending on the motherboard, even if the slots look the same, even if they physically fit.
What happens if you do?
Best case, the system probably won't even boot. Worst case, instability, random crashes, data corruption. It's a recipe for disaster. Always, always check your motherboard or server manual for supported memory types and configurations. Don't guess.
Solid advice. Okay, so this deep dive really shows that this memory stuff isn't random. It's all about very specific, purposeful engineering choices. Each type, UDIMM, RDIMM, LRDIMM, is a distinct solution tackling a specific problem, making calculated trade-offs between speed, stability, and capacity.
It really is quite elegant when you break it down. Which leads to a final thought for you to chew on, connecting back to something we mentioned earlier. We talked about that constant push for energy efficiency, like DDR4 running at just 1.2 volts. That's great for saving power overall. But then think about LRDIMMs. They let us pack memory incredibly densely for maximum capacity. We're talking dozens of chips crammed together on multiple modules right next to each other in a server chassis.
Yeah, that sounds hot.
Exactly. So the provocative question is this. As we push for both maximum memory density using things like LRDIMMs and lower operating voltages for efficiency, how are system designers actually dealing with the intense localized heat generated by all those densely packed components? How do you balance the need for massive capacity with the very real challenge of keeping things cool enough to run reliably and efficiently?
That balancing act, capacity versus heat versus power, feels like the next big puzzle in system design, doesn't it? Something to keep an eye on. That's all the time we have for this deep dive. Hopefully you can now decode those memory module labels with more confidence. Thanks for joining us.